All right, ladies and gentlemen, we have a related rates question here. So water is draining from a conical tank at a rate of 5 cubic meters per second. The tank has a height of 10 meters and a base radius of 5 meters. So the question is, how fast is the water level dropping when the water is 6 meters deep? Parker, go ahead.
Alrighty. So what we want to do here first is we want to find how do we even find the volume of the cone, right? That's going to be pretty important overall. So we know the volume of a cone is going to be V equals 1/3 pi r squared times h, right? Okay. Now, just as we're writing that, we also might as well write down our knowns and our unknowns, what we're trying to find, right? So what we want to find is the rate at which the water level is changing. And the way we're going to denote that is going to be dH dt for this problem. So dH dt is our unknown, right? I want to find that. Okay. Then what else does the problem tell us? That's always a good thing to know, right? We know that at the point we're looking at the point h is going to equal 6. So that's where the water is 6 meters deep at that point in time. We also know that the volume is dropping at -5 meters per unit t. And it's important to catch the negative there because we're talking about, right, negative, we're losing water, we're not gaining water. You're gonna go the wrong way if you don't catch that. So, what we're eventually gonna wanna do here, right, is if we're looking for dH dt, we're gonna have to take the derivative with respect to h here. But right now we have a v over here, and I really don't feel like, sorry, that's wrong. What I meant to say, we have an r over here. We really don't want this r in here, right? Because we don't have any r variables here that are useful to us. We don't want to have to take a derivative of r because there's just nothing to put in there. So what we want to do is we want to find r in terms of h. Now, luckily for us, this is a cone. And when you have a cone, cones are proportional. So we know that in a cone, r over h is always going to be proportional to itself, right? So in the information they gave us in the problem, we know that it's going to be 5 over 10, or 1/2 is where that simplifies down to, obviously. So, therefore, r is going to equal 1/2 h. Okay, now I'm going to erase that just so we have enough space. But just remember, r is equal to 1/2 h. So now what we can do with our volume equation over here is going to be v equals 1/3 pi 1/2 h squared times h, right? It's a lot simpler. We're only doing one changing variable on this side of the equation, not two. So we're going to go ahead and simplify that down. After you simplify all of that down, you're going to get v equals pi over h cubed over 12. Pi times h cubed over 12, I'm sorry. Now what we're going to have to do is we're going to have to go ahead and differentiate that, right? So dv dt, it's going to come out to pi over 12 times 3h squared dH dt. All right, now we can just start substituting in numbers, right? We love substituting in numbers. We know that dv dt is going to equal 5, right? -5, I'm sorry. So that's our dv dt. And then we're going to substitute in 6 for our h. So you're going to end up with pi over 12 times 3 times 6 squared dH dt. All right, and now all we really have left to do is solve for dH dt, right? So -5 is going to equal 36 pi over 4 dH dt. Now we're going to come back up here so we have enough space for everything involved. Okay, 36 pi over 4 times dH dt is equal to -5. So you're really just going to divide by 36 over pi times 4. You're going to divide -5 by that, which we've done the math already for you, so you don't have to. But it's going to come out to -0.176 meters per minute, or -5 over 9 pi. So that's going to be your answer. That's what dH dt is equal to. Hope you found that helpful. Thank you, guys.